together, I bring 3 and 4 together, and there's some set of operators propagating in the middle that are exchanged in the OPE. This gives me an expansion. I have this prefactor times sum over all the operators which propagate in the middle. And because I've used the OPE twice, I have product of 3-point functions, coefficients. And this multiplies these differential operators C acting on 2-point functions. Okay, so I get something like CI, x1, 2, del 2, CJ, x3, 4, del 4, acting on OI of x2, OJ of x4. And because this prefactor already has all the right transformation properties, sorry, this got wrong. It shouldn't be here again. I just inserted the OPE twice, so I just have product of C's acting on the 2-point function. But now we know that this object has to have all the right transformation properties to be a 4-point function. So it takes the same form that I wrote up here. With prefactor of x1, 2, the 2 delta phi, x4, the 2 delta phi, times functions of u and v, and I get one such function for every exchange operator. So now this function is of u and v is just what I get by evaluating these derivatives acting on the 2-point function, and it's labeled by the scaling dimension and spin of this operator O, and then by conformal symmetry, these are only functions of the cross ratios u and v. So in general, I can do this kind of expansion, and this function of u and v is what we call a conformal block. And contains the information about the spectrum of primary operators. It contains dependence on delta and delta.
Sorry, so just to be sure.
Yep.
Basically, G is C times that I that you are going to read.
G is C acting on this 2-point function.
Yeah, and the 2-point function is it was written as I there.
That's
so,
correct. Yep.
Okay.
Yep. So the 2-point function is written over here.
Okay. Okay. Yeah.
And this is what I get. Yeah. Up to this. I'm calling this prefactor, but otherwise that's what I get. And so if you just brute force work out what these differential operators are acting on 2-point functions, you can start evaluating the conformal blocks. Fortunately, there are easier ways to do it than that, which I'll tell you about in a second. But once you have this expansion in conformal blocks, now you can start. Now you notice the fact that here I picked two particular pairs of phi's to do the OPE, but this wasn't a unique choice. Okay, I could have also picked those pairs of phi's, and it would have given me a different expansion. Or another way to say it is that I started with an object which is symmetric under permuting the coordinates, but once I do this expansion, this permutation symmetry is not manifest anymore. And in fact, requiring that all these expansions equal, or requiring that this sum gives me something permutation symmetric, gives me a constraint. Okay, so graphically, I have some constraint that a sum over expansions like this has to equal sum over expansions like this. Or in equations, down here, get a sum and phi O squared G B has to equal an expansion over O and phi O squared times G V and U. So if I look at the constraint that this is symmetric that we're exchanging 1 with 3, then, as I said, U and V switch with each other under 1 gets exchanged with 3. And the only thing you have to be a little bit careful about is this prefactor sitting in front of the blocks, because it also transforms non-trivially under 1 goes to 3. And taking that into account gives me U over V to the delta phi sitting in front of this expansion. So, okay, so this is a very non-trivial constraint. And what is it a constraint on? It's a constraint on the allowed values of scaling dimension spins and 3-point function coefficients that every conformal field theory has to satisfy. And once we understand what are these conformal block functions appearing in this expansion, we can start studying this constraint and asking what does it imply about the spectrum. Now we did have this one caveat that we should only be able to apply these different OPEs for configurations of coordinates where both expansions converge. Okay, so if you think about this condition that you can draw a sphere separating the two coordinates that you're using the OPE from all the other coordinates, and ask what does this imply for U and V, then what it implies is that U and V have to be between 0 and 1. Okay, so this is the regime where both of these expansions are expected to converge. Okay, but modulo that, this is the constraint called crossing symmetry, and it leads to constraints on the set of scaling dimensions, spins, and OPE coefficients in CF. Okay, so this was just the constraint coming from one 4-point function, phi. In general, you have constraints from every 4-point function. Say 4-point functions of O, where all of these O's might be different operators, all of these O's might carry different Lorentz quantum numbers, etc. And the full set of Bootstrap constraints comes from acquiring crossing symmetry, or equivalently the fact that all these OPEs are equal to each other for every 4-point function. Now the idea behind the conformal bootstrap is, of course, use these constraints to solve CFTs. Now, Now it's not too hard. It's not too hard to write down crossing symmetric functions. Okay, so it's not too hard to write down functions of u and v that are invariant under exchanging u and v. So a delta. The more non-trivial thing is that when you take your function of u and v and expand it in conformal blocks, is to see that all of the coefficients of the conformal blocks are positive. Okay, so here if we're in a unitary conformal field theory, we can work in a basis of Hermitian operators where all of the 3-point function coefficients are real numbers. And if the 3-point function coefficients are real numbers, then their squares are positive. And that becomes a much more non-trivial constraint. Okay, the fact that I need to find a crossing symmetric function of u and v, that when I decompose it into conformal blocks in all possible channels, I always get positive coefficients. And this is really one of the powerful tensions that's going into the Bootstrap. That there's a tension between crossing symmetry and unitarity. By the way, another non-trivial constraint is that if I write down some random function of u and v and expand it into conformal blocks, you can ask, do the scaling dimensions of all those conformal blocks satisfy the unitarity bounds? That's also a non-trivial constraint. That all of the dimensions have to start from d minus 2 over 2 for scalars, or l plus d minus 2 for scalars. And so, okay, here, in this context, unitarity means that these coefficients are positive and all the dimensions are bigger than the unitarity ones. Now I say this is a tension. We can also turn it around and say, okay, I can easily write down some function of u and v that has positive coefficients, and the deltas satisfy the unitarity bound. They just sum up a bunch of conformal blocks with positive coefficients. But if I do that, then there's no guarantee that what I get will be crossing symmetric. Okay, so you can easily impose either unitarity or crossing symmetry, but putting them together becomes very non-trivial. Okay, so now how do we study these equations? Let me say there are both analytical and numerical approaches to doing this. We can either try to study this equation analytically, maybe by doing perturbation theory around a known solution. We can do it by going to some limit in cross-ratio space where the equations become more tractable, and so on. So there have been various successful analyses along those lines. The alternate approach is to just take this equation and put it on a computer and ask the computer, well, if I impose that this equation has to be true, what does it tell me about the allowed values of, say, the leading scalar operator dimension? And this approach has also led to very exciting results. So before we can do that, first I need to tell you a little bit more about what the conformal block functions are. Okay, so let me just ask, what are the conformal blocks? G sub delta L of u and v. And there are various ways to think about them. One nice way to understand what they are is that they're actually very nice group theoretic objects. In particular, they're eigenfunctions So, okay, the conformal group has some quadratic Casimir that commutes with all the generators. That Casimir operator has an action as a differential operator, coordinates, and the conformal blocks are eigenfunctions of that differential. So this leads to the statement that there's some differential operator in terms of U and V, which, acting on G, gives me the Casimir eigenvalue. Okay, so what is this Casimir eigenvalue? It's just some simple function, delta minus Z plus L plus 2, some simple function of the scale dimension and spin of the operator. And this is a second order differential operator in 2 variables. So actually, this Casimir equation, thanks to some very nice work of Dolan and Osborne, actually has very nice closed form solutions in some situations. And in particular, their closed form solutions in even space-time dimensions. 2, 4, 6, this is work by Osborne. 3. And so let me just write down what those look like. So 4 dimensions. The conformal blocks. First of all, it's a bit simpler to express them in terms of variables Z and Z bar instead of U and V, where U is U Z bar and V is 1 minus V, 1 minus Z bar. And in terms of these slightly different variables, the conformal blocks just look like a product of hypergeometric functions. So it looks like this coefficient Z bar over Z minus Z bar times function K, that I'll define in a second. K sub delta plus L of Z, K sub delta minus L minus 2, Z bar, minus, when I get my switch Z to Z bar. And what is K? K sub beta is Z to the beta over 2 times the 2f1 hypergeometric function of beta over 2, beta over 2, beta Z. Okay, so that's it. So by solving the Casimir differential equation, you see that it has this solution. You have to come up with the right change of variables to get there. And maybe I should say that these Z variables have a very simple interpretation. You can always, I have 4 points. I can always do a conformal transformation to put one of the points at 0, one of the points at 1, and one of the points out at infinity. And then what's left is the location of the last point in a plane, in a two-dimensional plane. And if I write the position of this point as a complex variable Z, then this Z in the complex plane is the same as this Z. So if I do a conformal transformation to put point at 0, 1, and infinity, then the last point can be confined to a two-dimensional plane, and its position is what is the so the region where both of these expansions converge is where value of z is between 0 and 1. Actually, the conformal blocks themselves are nice, smooth, analytic functions outside of this. And in particular, if you think about the analytic properties of hypergeometric functions, they have a branch cut in the complex z-plane. There's a branch cut starting at 1 for this hypergeometric function. But everywhere outside of that branch cut, this is smooth and analytic.
And is this equation expected to be valid even outside, now that you have an analytic continuation?
Is which the crossing equation?
Yeah, the crossing.
Well, the problem. I mean, this expansion, the sum over blocks doesn't converge. So certainly, if I went outside of that region of convergence, if I did an analytic continuation of this function outside of its region of convergence, that would be should be the same as the analytic continuation of this sum outside of its region of convergence. But that, in practice, that's very hard to do.
Is there a sense of orthogonality for these? That you have a function of your idea can expand on this natural way of extracting the coefficients.
It's hard. So if this were a compact group, then that would be straightforward to do. But because this is a non-compact group, it's more subtle. I think there's, for example, there are nice orthogonality relations if you go to imaginary scaling dimensions. But when they're real parameters, it's harder. So it's something that many people in Bootstrap have thought about and tried to make sense of, but I don't think anyone's really succeeded.
Excuse me.
Yeah.
How general is this result for the conformal group? Did we make some assumption about the operator part?
So I assumed it was a scalar operator.
And any conformal dimension for that?
And that's right, yeah. I assumed it was a scalar operator of arbitrary conformal dimension. I assumed it was a primary operator. And as you can see, actually this block doesn't depend on delta phi. Okay. Actually, in more general situations, that's sort of an accident. In more general situations, if I have, say, 4 different scalar operators, then the conformal blocks start depending on the differences in scaling dimensions. But in this simple case, okay, yeah.
How is the differential equation connected to 4-point function?
Good. So let me let me answer that in one second. So let me first say, in general dimensions, including 3, which is a very interesting case, there's no closed form, no? So you have to have come up with some other trick for evaluating the blocks. And so let me just mention a general approach to doing that, which will make the connection to the Casimir clear. So another way I can represent the blocks is that they're what I get if I start. I take my 4-point function, and insert this way a sum over intermediate states. And I want this to be sum, where what I need to do is sum over an intermediate state, which is the primary operator O, but I'm also summing over all of its descendants, PO and PPO, and so on. And to do this sum properly, I should make sure that I'm summing over normalized states. Okay, so I have to normalize these states alpha to 1. So this is another way I can represent the block. It's a sum over the contributions of the primary O and all of its descendants to the 4-point function. And actually, this representation makes it clear why G should satisfy a Casimir differential equation. Because one thing I can do is insert the Casimir operator, I'll call it L squared, into this expression. And I can either act with L squared to the right, in which case it gives me some differential operator in x3 and x4, or I can act with L squared to the left, in which case it gives me the eigenvalue of the state alpha. Right? But because L squared commutes with all the generators, it has the same action on the primary as all of its descendants. So acting to the left just gives me the Casimir eigenvalue, acting to the right gives me the differential operator in 2 variables. Okay, so this is one way of representing the block. Now one thing that's kind of interesting about this expression is that something funny can happen if one of these alphas becomes a null state. Okay, so in particular, if the 2-point function of an alpha goes to 0, then that contribution to the sum will blow up. And in terms of the conformal block, this shows up as a pole. So the conformal block has a pole if alpha is a null state. And this means that G of delta L goes like 1 over delta minus some critical value of the star, where there's a coefficient. Okay, this delta star is the dimension. Remember, delta is the dimension of the primary operator. So we're saying that if delta takes a value such that it has a descendant which is a null state, then you expect a pole like this. And further, because if there's some descendant which is a null state, all of its descendants are also null states. And under conformal transformations, the null states can only transform into each other. They can't transform into non-null states. Which means that the null state, together with all of its descendants, form a representation of the conformal curve. And because of that, it means that the residue of this pole